7. We need to show that the telegraph signal is a street-sense stationary process. And from the lecture notes here, we have known that if X is street-sense stationary process, then we have the time invariant shift property, which is the probability of ytn equals to yn, ytn minus 1 equals to yn minus 1, and etc. to yt1 equals to y1 is equals to the time shift by eta, which is ytn plus eta equals to yn. Ytn minus 1 plus eta equals to yn minus 1 and etc. to yt1 plus eta equals to y1. So if we can show that the random telegraph signal meet this property, then it is a street-sense linear process. And for the above equation, we have it is valid for any n, any t1, t2 to tn, and any eta. And since we know that the random telegraph signal follows Poisson process, which is the current state is independent of the previous many state, and it is only dependent on the previous one state. So we can rewrite the probability of y at tn. The probability of y at tn equals to 1, condition that yt minus 1 equals to 1, yt minus 2 equals to 1, till yt1 equals to 1. And because we have seen that it's only dependent on the previous one state, so this conditional probability only depends on this term. So we can rewrite this probability as the probability of ytn equals to 1 condition. It's the condition that yt minus 1 equals to 1. And based on the slide notes, we know that it is equals to this formula, which is only dependent on the tn and tn minus 1, the difference between tn and tn minus 1. So if we combine the total equation, we know that the probability of ytn equals to 1 and ytn minus 1 equals to 1 and etc. and yt1 equals to 1 is equals to let me make the previous part smaller. We can expand this equation by the multiplication of a series of conditional probability. So it is equals to the probability of ytn equals to 1 under the condition that ytn minus 1 equals to 1, ytn minus 2 equals to 1, till yt1 equals to 1 times the probability of ytn minus 1 equals to 1 under the condition that yt minus 2 equals to 1, ytn minus 3 equals to 1, and etc. till yt1 equals to 1. T1 equals to 1. And times and so forth. The last term is yt1 equals to 1. And since previously we have derived that this equation is only dependent on this term, so it can be rewritten as the probability of ytn equals to 1 under the condition that ytn minus 1 equals to 1. So we can rewrite this equation to be the conditional probability of ytn equals to 1 under the condition that ytn minus 1 equals to 1 times the conditional probability that ytn minus 1 equals to 1 under the condition that ytn minus 2 equals to 1, and etc. till the probability of yt1 equals to 1. And this term only dependent on tn minus 1 as we have derived here. So the above equation, if we shift the above, let me make it smaller. So if we shift the above equation by time interval eta, we have tn minus 1. This is only dependent on shift by eta. We know tn minus 1 is equals to tn plus eta minus tn minus 1 plus eta. So it will not change the value of all the terms stated above. So we have shown that this equation is equals to this equation, and in this way we have shown that this is a straight line stationary process.